So in this first part, we're going to look at probabilistic models. And basically, the idea is to give a brief review of graphical models. We saw this in machine learning last semester. I'm going to just revise this briefly. And then I'm going to focus on the restricted Boltzmann machine and see how we can implement and train one. And also related to that, this method of deep sampling, which allows us to sample from the probability distribution of a probabilistic model like a restricted Boltzmann machine. So let's start with this idea. We saw so far, we've been focusing on models that try to discriminate between, for example, different classes. You did that in the assignment, for example. In general, these discriminative models try to learn conditional probabilities. That is, we have some target value, something that we are predicting or outputting from the model, that is conditionally dependent on the input into the model. And this is enough if we want, for example, to train a classifier. So in that case, all we want to get from the model is an idea of what is the class, for example, for given the features that we present to the model. But if we want to generate examples, this is not enough. So if we want to be able to extract a sample from our model, particular examples, we need the joint probability distribution of both the features of each example and whatever other label that we have, for example, the class that it belongs to. Now, there are some approaches that we are going to see next week, or in 2 weeks, variational autoencoders, generative adversarial networks, and so on, that solve this in a particular way. But with these probabilistic structured models, we try to capture explicitly the relations between the different variables that give us the relevant distributions. And graphical models are a good way of representing these relations. So the idea here is that if we have many variables, if we need to take into account all the possible combinations, then this will give us a huge space, and it will be very hard to learn anything from real data, because we would need a huge amount of data. For example, if we have n variables and they are discrete, each one has k values, then we have k raised to the power of n combinations. And if we need to estimate the probability distribution overall of these combinations, we will need a huge data set. But with graphical models, we can specify which combinations are relevant, which relations between variables, and so reduce this space. One example of graphical probabilistic models are Bayesian networks that are directed acyclic graphs that express how the variables are related in the sense of being conditionally dependent on others. So these errors means that the variable that is receiving the error is conditionally dependent on the variables from which it's getting this error. So this is what we are representing here. For example, the probability of x3 having each particular value, or the distribution of probabilities here in x3, will depend on the values of x2 and x1. And this is what we are expressing here. This allows us to write the joint probability distribution by going along the graph. So we start with the marginal distributions of these. They have no ancestors, so they just have their own probability distribution, and it does not depend on other values. And then we have other variables that are conditioned on the values of their ancestors and so on. So we can write the joint probability distribution not by looking at all possible combinations, but just by those relations of conditional dependence that we express here on the graph. And this is useful if we want to express things like causal relations. For example, the probability of having cardiovascular disease may be dependent on stress. It may be dependent on whether someone smokes or not, or in this case, we also consider that stress is a factor that will affect the probability of smoking, and sedentary life will depend on income and things like that. So we can express relations between the different variables and build a probabilistic graphical model in this way. So these are for Bayesian networks where the relations are directed. There is one variable that is conditionally dependent on the other, and the graph must be acyclical, otherwise we would not be able to write those conditional dependencies. Another type of graphical models are these Markov random fields, where we use the edges on the graph to express that these variables are not independent, they depend on each other, but we don't use directed edges. So we are not saying which one is conditional dependent on the other, we are just saying that they are related in some way. And since if we know the value of one variable, we can block the information from the rest of the graph to other neighbors. For example, if we know the value of x3, then there is nothing about x4, x5, and so on that can affect x1, because this one is already fixed. So there is nothing over there that will affect the probabilities of x1. This means that we can decompose the giant probability distribution of all these variables by considering only the maximal cliques, which are the groups of variables that are all interconnected. For example, this is a maximal clique, because it's a clique, all of these variables are related to each other, and we cannot add more variables while still remaining a clique. So this is an example of maximal clique, this is another one, and so on, and we can use these to compute the giant probability distribution over all the variables. Now, if we use for each clique some non-negative measure of the tendency to be in each particular state, so there is a function depending on the state that gives us how propense those groups of variables are to be in that state or not, then we have this unnormalized probability distribution, which is like a probability distribution. There are no negative values. Higher values indicate more likely combinations, but since it's not normalized, it doesn't add up to 1, it's not really a probability distribution. However, if we take the sum of these normalized propensity function over all the possible states, and we divide by that, so this would be the partition function, then this is normalized, and now it adds up to 1, and it's a probability distribution. So basically, if we have this kind of function that measures the tendency of the system to be in some particular state, we can create these probability distributions and depending on those functions. So one type of approach for this is inspired in physics, in thermodynamics, and uses some energy function. Some states are in higher energy than others, and the unnormalized probability of the system being in those states will decrease exponentially as the energy increases. So this is related to thermodynamics and physics. Higher energy states are less likely than lower energy states. So this would be the function that we can use for the unnormalized probability distribution, e raised to minus the energy of x. So this is always positive. And all we need is to use some normalization, use the partition function to normalize and get the probability distribution. It's also practical if we use the logarithm of this normalized probability distribution, because then this e raised to that power, the e disappears and the expressions simplify a lot. So when we use these Markov random fields using this type of function, based on this concept of energy, then these are called Boltzmann machines, because this is the Boltzmann distribution from physics. Okay, so one issue here is once we describe one of these models, we have all the parameters, the functions, the connections between the variables. How can we use that description of the distribution of probabilities of all the variables to sample and obtain some possibilities, some examples from that? In the case of Bayesian networks, since these are directed graphs that show conditional dependencies, we can simply start with the probability distributions of these variables, sample from those, and then go through the graph, because once we know the value of x2 and x1, we now know what the probability distribution is for x3. We can sample from that one and go on. So basically, for Bayesian networks, this is simple because we have a natural sequence to follow through the graph in a way that at each point we can determine what is the probability distribution, because we know what we need for that from the ancestral variables. For Markov random fields, this is more complex because we don't know where to start. There is no direction here, and these variables are dependent on one another, these are dependent on one another, and so on. So we cannot do this in such a simple way. But there is one method, this Gibbs sampling method, that consists in starting with some random values here without taking into account the probability distribution that is given by the model. And then for each variable, we can simply consider the values that have been assigned to the others to which the variable is related. For example, if we want to sample now from x2, we consider the values in x1 and x3, use those as a starting point, and resample x2 given those two values. And now we do that for all the variables using the initial values for all the variables that we need when sampling each one. And now we can repeat that and repeat, and as we do this iteratively, we start with something that is very far from the probability distribution the model gives, but as we iterate, we approach more and more what would be the more probable states according to the model. So this is the idea of Gibbs sampling that allows us to extract from one model of this type, the Markov random field, examples that follow the probability distribution expressed by the model. Okay, so let's look at the specific type of Boltzmann machine. So remember, a Boltzmann machine is a Markov random field that uses that energy, e raised to minus the energy, as the unnormalized probability distribution. A restricted Boltzmann machine is a Boltzmann machine that is a bipartite graph which separates the variables that we can observe, the observable variables, and a set of variables that we cannot observe, the hidden variables. And this is bipartite in the sense that all the connections, all the relations are between the two groups, and there are no relations within each group. So if we can build a graph like this, all the connections are between hidden variables and observed variables, and there are no connections between observed variables or between hidden variables, then if we use that energy function, we have a restricted Boltzmann machine. So this has interesting properties for learning and for expressing these probabilistic models and for learning them from data, and we're going to see how to implement one of these. Now, this is not a deep model in itself. As you see, basically we have one hidden layer and one observed layer, but it can serve as a basis for deeper models. For example, deep belief networks, which can have several of these hidden layers, and then have a directed relation between one of the hidden layers and the observed variables. So in this case, these are directed edges because they have this conditional probability relation, like the Bayesian networks, or deep Boltzmann machines that are Markov random fields, but they have these different layers, so we can partition them in different layers. We're going to see the simpler example where we just have a restricted Boltzmann machine and see how we can implement it and train it and use it, for example, to denoise the image. So in this case, we have the probability, the joint probability of the variables, or the probability for a given state, that is, the vector of observed variables is this particular one, and the vector of the hidden variables is this particular one. This is the normalization constant there, so basically using the partition function and summing over all the possible states. And this would be e raised to minus the energy of this combination. Now we can use for the energy one function like this, which is, we have here a bias for the value of the observed variables, a bias for the hidden variables. So basically these two terms gives us the tendency of those values to be high or low, depending on the value that we put there. And then we have the interaction between observed and hidden variables. Remember that in a restricted Boltzmann machine, we only have connections between the hidden variables and the observed variables. There are no interactions between the observed variables and no interactions between the hidden variables. So this is expressed here, the propensities of each of these variables to be high or low, and here the interaction between them. So we have a matrix with weights for all of these combinations that you can imagine to be the same as the kind of matrix that we used in the first tutorials to model the layers of the neural network, where you have the different neurons and each neuron has a number of weights. So basically it's this type of matrix. So we can represent this with these sums or with vector and matrix operations, where we do the inner product of these vectors and the product of this vector by the matrix and the other vector of the hidden values. This is similar to what we did with the neural networks when we started modeling it in TensorFlow. So we can, since we have edges only connecting the hidden to visible units, we don't have edges within them, we can actually separate this into the two blocks. We have the probabilities of the hidden units given the observed values, and the probabilities of the observed values given the hidden values that we have there. So we can write, we have this relation between the joint probability distribution and the conditional probabilities. So basically we can write this, and for the conditional probability of the hidden values given an observation, a vector of observed variables, we can write this from the joint probability distribution. So it would be this one divided by the probability of that particular vector of observed values. So looking at the previous equations, we can write this expression here. So basically we have this normalization constant, and this would be the unnormalized part of the probability distribution, but basically we are using the biases for the hidden values here for these hidden variables, and then multiplying the matrix for the observed variables and the weights corresponding to each particular value on the hidden layer. So basically this is this is analogous to what we've been doing with the layers on the neurons, where we are using all the weights for the unit j, the hidden variable j, multiplied by the vector that we have in observed values. We can do the same thing also for the observed values given the hidden layer, and this would be something that is not really what we do with the normal dense layers, because we don't have this notion of the joint probability distribution that would allow us to go back and forth. So this is where we have a difference in this probabilistic model. Since we are modeling the joint probability distributions, we can compute the conditional probability of the hidden values given the observed ones, but we can also do the reverse and compute the probability of the observable values given the values on the hidden variables. So basically, when we simplify this expression, we get this if we consider a simple case where the values of these variables are just 0 or 1, they are binary. If we consider the probability of the value of one particular hidden variable being 1, given the vector of observations that we have, so given an example, we have the probability of the unnormalized probability here, given by the energy function, divided by the partition function, so this z prime here, which is basically the sum of the unnormalized probability when the value is 0 and the unnormalized probability when the value is 1. So these are the two possibilities, and when we divide the unnormalized probability function by the sum of these two, we are normalizing it and we get the probability. So since the unnormalized probability function is this e raised to the energy that we have there, and we have the probability of the value being 0 would be just e raised to 0, because this would have a 0 value on the energy term here. This e raised to 0 is 1, so we have e raised to something over 1 plus e raised to the same thing. This is a sigmoid function. So in this particular case, when we have these binary variables, the probability of h, the value of this particular hidden variable being 1, is given by the sigmoid function applied to that energy term that we have there. So if we want to use this conditional probability for the different values of h, we can consider the case where h is 1 or h is 0, and this is basically just a trick, so that if h is 1, this is 2 minus 1, so it's 1. If h is 0, this is 0 minus 1, and it's minus 1. We are just inverting the sign here, because the probability of being 1 is 1 minus the probability of being 0. So if we multiply that by this and apply the sigmoid, we have the probabilities of being 1 or being 0 depending. We can do this similarly for v, and we get, so basically the whole thing is similar, only we are exchanging h and v there, and we get a similar result, only now we have, here we have the bias for the hidden neurons, and we are multiplying the transpose of the weight matrix by the examples we are observing. Here we have the bias for the observable variables, and we are multiplying the matrix as it is by the values of the hidden variables. But other than that, this is very similar. We obtain the same expression. Okay, so what's the use of this? We can now use this to train the restricted Boltzmann machine. So the probability of this Markov, the probability distribution on a Markov random field in general will be depend on all the variables that we have. So this x is general, doesn't matter if they are hidden or observed, whatever, and the parameters that we have for all that energy function and the relations between the variables. And this probability will be the unnormalized probability, so basically what we compute with all the energy, divided by the partition function that makes everything add up to 1. That's what converts the unnormalized probability into a probability distribution. So if we want to maximize the logarithm of the probability, this is the maximum likelihood approach. Basically, we want our model to have a probability distribution as close as possible to the actual data that we are using. Then what we need to do is we need to maximize this expression, which is the logarithm of the unnormalized probability minus the logarithm of this partition function. So the sum of the probabilities over all the sum of the unnormalized probabilities over all the states. And so if we are trying to go down this function to minimize this, or to maximize this likelihood, sorry, in this case we go up this function, We can look at the gradients here. So this would be going up the gradient on the logarithm of the unnormalized probability distribution and going down the gradient on the logarithm of the partition function. And this, we can imagine this, that we are trying to maximize the probability of the data that we have while minimizing the unnormalized probability that the model is assigning to everything else. So we have this positive phase where we try to maximize the unnormalized probability of the data, and the negative phase where we try to minimize what is often called the hallucination. So this would be the model giving the values of unnormalized probability that are high for states that never occur. So the model basically is tricking out, is hallucinating and making things up that don't exist. So we have these two phases, positive and negative, that we can alternate. We change things to try to maximize this and also try to minimize that part of the partition function. Okay, so let's bring this together here. This Z, remember, is the sum of the unnormalized probabilities over all the states. And this leads us to the contrastive divergence algorithm for training a restricted Boltzmann machine. So we start with an example. We have a sample of the observable values, and we can compute the probabilities of the hidden values and extract a sample from those probabilities. So now we have a sample that we observed. We have a sample extracted, a sample from those probabilities of the hidden values, and we can now compute this positive gradient, which would be, so this part here would be the outer product of the values that we have on the example and the values that we have in the hidden variables. So both of these are vectors. If we compute the outer product, we have a matrix, and this gives us an idea of how to change the weight matrix, in which direction, in order to maximize the probability of this example occurring in our model. So this would be the positive stage here, where we are maximizing the unnormalized probability distribution for each particular example. And now what we need to do is to minimize this part, but this would be trying to minimize over the whole set of possible states on our model. So we need some way to sample from the possible states in our model. Basically, we are looking for the hallucinations, the things that our model can make up and may not be correct. So that's where we can use Gibbs sampling. Now we have an initial value for V and for H, so we can assign an initial value on the variables of our model, but we want to sample a set of values that is closer to what the distribution is that our model is currently representing. So we're going to start from those, and we're going to use Gibbs sampling. We're going to iterate until we obtain, after some iterations, we obtain a new set of values for the observed and the hidden variables. We don't need many iterations because we are already starting from some observed values, and hopefully as our model trains, those become closer to what the model considers to be high probability. So we generally don't need many iterations for this, but we now have a sample of what the model usually dreams of. And now we want to minimize that as we maximize the probabilities of obtaining real values. So this would be the outer product of this hallucination, so to speak. And now this gives us the negative gradient for the W. So this is what we want to suppress. We want to suppress the model making things up, and we want to incentivize the model approximating the data. So the update would be the difference between the two, and also the biases would be updated by the difference between the actual observed values and the hallucination of the model, and the hidden values that we obtained from the observed values, and what the model hallucinated for the hidden values. Okay, so we can use this to adjust the parameters of the model, the biases and the weight matrix, in order to maximize the probability of real data while minimizing whatever different things the model may make up from those parameters. So let's see how to do this in practice. This is based on a demo on this book, if you want to take a look there. And basically, we're going to train a restricted Boltzmann machine on NIST. This would be unsupervised learning, because what we want is a probabilistic model that represents, that captures the way the distribution of values in NIST. So remember that NIST is a set of images, 28 by 28. This is we can convert this into vectors of 784 values. So basically we are discarding the labels. We don't care if it's a 1, a 2, or whatever. We just use the train and test data here. We convert this into matrices with 784 columns. And now we create a restricted Boltzmann machine that would have 784 visible values. These are the data, the images that we are feeding, and has 200 hidden variables in that other layer, the hidden layer there. So this is our restricted Boltzmann machine. And now what we need is compute the probability of a hidden variable being 1 given an example, an image of NIST, so a vector of the observed vectors. And this would be the sigmoid applied to the product of the weights matrix that we have there, multiplied by the vector of visible, of observed variables, plus the bias for the hidden, variable. So basically, this would be a vector for all the hidden layer, and we would obtain the vector of probabilities for the hidden values. The same thing can be done to compute the probability of a value on the observed layer being 1, given the vector of hidden values there. So another multiplication, but now we are transposing the weights matrix and then adding the bias for the visible or the observed values. So basically, these two functions are just what we saw here for these conditional probabilities. So if we have an example of observed values, we can compute the probabilities of the hidden values being at 1. If we have the hidden values, we can compute the probabilities of the observed being at 1. Also, we can, once we have these probabilities, so all of these are, this is a vector of values between 0 and 1, giving the probability of that variable being 1, we can use that to sample at random from that probability distribution and get all the values that are 1. So we take the probabilities, we subtract a random dice, a random throw of the dice, which is basically a vector of a uniform distribution between 0 and 1 with as many elements as the probabilities that we have here. And so this will be positive if the probability is higher than the roll of the dice, and it will be negative if the random value is higher than the probability. So we take the sign of that. The sign gives us a +1 or -1, depending on whether this is positive or negative. And the ReLU here is just for convenience. This is not really as an activation function, but it's just so that if the sign is positive, this is 1, and the ReLU of 1 is 1. If the sign is negative, this is -1, and the ReLU of -1 is 0. So it's just a trick to go from the -1, 1 to 0, 1, which is what we want for sampling. So basically, we are throwing the dice here to get a sample of 0s and 1s that follow the probabilities that we are supplying, and the probabilities can be computed depending on whether we have the hidden variables and want to compute the probabilities of the observed ones, or vice versa. Now we can use that for deep sampling. So we receive here we want to do these iterations. We receive here a number of iterations that we want to do, and we receive a batch of examples here. So now we're going to compute, the batch of examples is of observed variables. These are the examples, are the parts on the visible part of the model. So we're going to compute the probabilities of the hidden variables being set at 1, given that batch of examples. Note that this is not necessarily just one vector, it's a batch of vectors. So actually what we have here is a batch of states, each one with its own probabilities for the hidden variables. Now we're going to sample from those and get the hidden states. So basically zeros and ones for the hidden variables for all the examples on the batch. And this would be the original one. So if we go back here to the algorithm, this would be from a sample, compute the probabilities of H, and obtain a sample of the state of the hidden variables. And now we're going to do the Gibbs sampling by starting from those states and now computing the probability of the observed variables given those hidden states, sample from the observed variables, and recompute the probability of the hidden states and resample from the hidden states. So now we're going back and forth and do this k times, changing and resampling all of these and recomputing the probabilities. So eventually this will converge to something that the model thinks it's most likely, but we can do this a k number of times. By default it's 1, but we can do a bit more, and then return the original, because we're going to use that in the contrastive divergence algorithm, and the hidden and visible states after Gibbs sampling, after these iterations. Okay, so now the training loop is like this. I'm using this approach that is not very elegant from a programming perspective, but it's very practical. The same thing that we used initially, we create global variables with the weights and the biases. And now for each epoch, we're going to fetch each batch along the training set. So basically, we have the start and the end of the batch by using the range on the start, starting from 0 until the end, and the end starting from the batch size until the end of the data set. So basically, the first iteration will start at 0 until the batch size. The second iteration will be from the batch size to batch size plus batch size, and so on, and all the way until the first one finishes. Because when you use zip ends when the first array ends, so you don't need to worry about where this will finish. Now we get a batch. So a batch is from the data set between the start and the end of the batch. We use Gibbs sampling to get the original state for the hidden variables for that batch, and the hidden and the observed states after Gibbs sampling, after doing those iterations. Now we have the positive and negative gradient. So the positive gradient is obtained using the data that we are observing multiplied by the original state of the hidden variables. And then the negative is the one that we obtain by using the values of the hallucinations that we got using Gibbs sampling. So basically, we are trying to maximize this part, that is the match between the probabilities estimated by the model and the actual data that we have. And we are trying to minimize the model making things up. So if they are different, then we should penalize those. Now this is just the batch size, so that we take the average here. Remember that when we do batch training, we compute the contributions of all the examples and then use the average of that for the gradient that we're going to apply. So this is what we're doing here, because all of these are being computed for the batch. But now we have the batch size. This is simply the shape of the batch that we have there, and we use that to rescale the update that we're going to do on the matrix of weights. So basically, the weights are going to be updated by the learning rate multiplied by this scaled vector that tells us where to go here. The same thing for the biases, so the biases of the observed and the hidden variables. We just take, in the case of the observed ones, the difference between the actual values on the batch and the hallucinations generated by the model, so what we obtained by Gibbs sampling, and for the hidden variables, we take the difference between the original hidden states and the hallucinations obtained by the Gibbs sampling. So basically here now we just take the mean of the error by doing the difference between what the model was generated by Gibbs sampling and what we observed, and we can report that, but anyway this is just for printing this out. This is the actual training loop using contrastive divergence. Okay, so now to train we use the training data here. So we start by creating our matrices. The matrix of weight is a matrix that has as many rows as the number of visible values on the observed layer, and as many columns as the number of variables on the hidden layer. And then we have the biases for the hidden and the observed ones. Note that we can start all of these at 0, because we don't have that problem of breaking symmetry that we have with neural networks. So this is similar, the kind of operations that we are doing, but since we are computing these different states and sampling at random and so on, we don't need to start these values at random, we can just start at 0. We are not doing gradient descent by computing the gradient of the activation functions and so on, like we do with neural networks. Okay, so now we train using the training data and 50 epochs, and now we can, after training, create a function just to reconstruct an image from some set of data. So basically what we do is, given an image here, a vector of observed values, we can compute the probability of the hidden variable being at some particular state, and use that probability to then compute the probability of the visible, of the states of the visible layer. So basically we are just using the sigmoid on the hidden layer, using the multiplication with the weights, and then going back again with the sigmoid for the observed layer. And this gives us an idea of what the model gives us back, or the probabilities of being each pixel set at 1 when we give an image to the model. So let's see what happens if we do this to reconstruct noisy images. So let's create a plot where we show the different images, and the images can be we take the sample, the 10 images from our test data. We create noisy versions of the image by using, for example, 2% probability of setting the pixel to 1. And then we reconstruct the original image and the noisy image. And we can show these as plots. So this is an example. This is the original image that we feed into the restricted Boltzmann machine. And this is what it gives us back as the probability of each pixel being set at 1 when it outputs the probability of the observed values. But if we feed in the images with noise, so you see here random noise, it still gives us back something that is mostly denoised. So it knows, so to speak, what is the most probable value of the visible variables there for that particular input, even if the input is not quite correct. So one application for this kind of models is denoising data. Another thing that we can do is using Gibbs sampling. Once the model is trained, we can use Gibbs sampling to see what the model is dreaming of. So what are the values that are, or the distributions that are represented there. So basically we can create a noise image, and then we can do different iterations for Gibbs sampling. What I do here is I start with 1, and then multiply by 10, do again with 10 iterations, 100, 1000, and so on. So we can see what happens, and then again, this is just to plot the result. So this is the original image. It's just noise in each case. I generate noise at random. And then this is one iteration of Gibbs sampling, 10, 100, 1000, and 10,000. So you see that as we start repeating, things start to converge, and eventually it converges to something that looks like a 2. So this would be basically what the model assumes numbers look like in general. The most probable kind of number is something that looks a bit like a 2. If we start from a specific image, then we can do this again, if sampling. If we do a few iterations, this happens, but then eventually it will all converge to 2. So basically, we can see what the model thinks of numbers. Numbers are something that look like 2, but if we don't do many of these iterations, we can add some variations a bit of those numbers. Okay, to sum up, we saw a brief revision of these graphical models, and then we focused on the restricted Boltzmann machine to give you an example of something that is similar, related to what we've been looking at, neural networks and so on, but it's different in the sense that we are trying to model probability distributions between what we observe and that hidden set of variables that we are using to capture some kind of structure in the data. And we saw the contrastive divergence algorithm. So basically we are trying to maximize the anormalized probability the model is assigning to the actual data, while minimizing the total anormalized probability of the model, represented here by a sample that we obtained using Gibbs sampling. So basically minimizing the hallucinations and maximizing the actual data. I recommend that you take a look at these sections of the book. And also, if you want, I've been using Gibbs sampling here as an example because it's very simple to understand. It's a simple algorithm. It's not necessarily very efficient. So if you want to learn a bit more about this is a good paper for other ways of getting samples from restricted Boltzmann machines. So if you're interested, you can look at that.